Welcome to the second lecture in our seventh module. As you'll recall, in the first lecture we discussed probability distributions for discrete variables. In this lecture we're going to be talking about probability distributions for continuous random variables. So a continuous random variable has a numerical scale and it can take on any value in an interval. In practice though, we're limited to the level of precision of the particular measure. For instance, if we're talking about dollars, then dollars, maybe cents if we care about cents. Minutes, it would be another example. Inches would be another example, etc. And with these variables, we use the measures of central tendency and dispersion that we discussed in a previous lecture. A probability distribution for a continuous random variable is specified by a probability density curve, also referred to as a frequency curve. Areas under the probability density curve between two chosen variables that you might care about on the horizontal axis are probabilities, and those would be indicated by the numbers on the vertical axis. And so the way that you actually measure these is using integral calculus. Don't worry, we're not going to do this. We're not going to use integral calculus in this course. Another thing to know is the total area under the probability density curve is equal to 1 because the probability must sum to 1. And so if you want to think about the shape of these probability distributions, there are several ways they might appear. The normal distribution is shaped like a bell. It's symmetric about the mean, median, and mode, has a single mode. This is where we're going to focus in this course. Unimodal has only one major meaningful peak, but it doesn't necessarily have to be distributed in the same way that the normal distribution would be. Bimodal, this is less common. This is a distribution that has two major meaningful peaks. Symmetric simply means it looks approximately the same on one side of the center as the other. And then the term skewness is used to describe how unsymmetrical a distribution is. So let's talk about that briefly. A right-skewed or positively skewed distribution is shown on the lower left-hand corner there. And as you can see, the bulk of the data is on the negative end of the scale, but the longer tail trails out towards the positive or right end of the scale. A left skewed or negatively skewed distribution, in this the bulk of the data is on the positive end of the scale, but then the longer tail trails out again towards the negative or left end of the scale. And then you can see in the center there what a symmetric distribution looks like. Okay, so let's talk about the normal distribution. Sometimes it's also referred to as the Gaussian distribution. And so in the normal distribution, as I mentioned, it's perfectly symmetric. The mean, median, and mode are all at the center. Because it's a probability distribution, it sums to 1 or 100%. And so 50% of observations are on one side, 50% are on the other side. You can see the formula for the normal distribution in the upper right-hand corner there. Don't worry about that formula. It's just what it is, but you don't have to memorize it. There's a normal distribution for each pair, mu, the population mean, and sigma squared, the population variance. And many variables that we encounter in real life are distributed normally in the population. A good example is body mass index. So, in addition to the normal distribution is the standard normal distribution. And this is important. Our focus is going to be here on the standard normal distribution. And so we use this standard normal distribution to standardize our variable x that we're interested in and then find its probabilities in a handy table. And so there's no need to calculate probabilities for normally distributed variables by hand or to use integral calculus. Lucky for us. So the standard normal distribution is a normal distribution. It's shaped the same way as the normal distribution. Same characteristics of the normal distribution are true of it. The difference is it always has a mean equal to 0 and variance equal to 1. And so if x is our random variable with a population mean of mu and variance of sigma squared, then we convert x to the standard normalized variable z. And so z is equal to x, whatever the value is, minus the mean, the population mean, mu, divided by the standard deviation, sigma, which is simply the square root of the variance, sigma squared. And z has a mean of 0 and variance of 1. And so this is great because frequently we're interested in what the probability is that x is greater than or less than some value. And so once we convert it to z, instead of looking for the probability of whether x is greater than some number, we can look for the probability that z is greater than some number. And to do that, we use the standard normal distribution and our handy table. And I've shown part of that table below. The entire z table is in your textbook in an appendix. And so as you can see there in the distribution, on the horizontal axis, the z-score ranges. Most of the z-scores between -3 and +3. 0 is the mean. 1 is the variance, and the square root of that is also equal to 1, which is the standard deviation. 0.5 or 50% of the values fall on the left side of 0, so between 0 and -3 z-score. 50% fall on the right side between 0 and 3. One thing I'll mention here is that in the z-table you'll just see positive values. So this is listing. So when you get a negative z-score, just convert that to the positive value to look it up in the table. The table always shows you for whatever given z-score. Say our z-score were equal to 1, and you look on the table there, and the probability is 0.3413. That is the probability that a given score falls between, the value falls between the mean 0 and a z-score of 1. So if you're looking to know what the probability is that it would be greater than 1, then what you would want to do is recall that the entire right side of the z distribution is probability of 0.5, so you would subtract 0.3413 from 0.5 to get that probability. We'll walk through that here in a minute. Okay, so here's an example. Systolic blood pressure in a healthy population, normally distributed, a mean of 120, standard deviation of 100. What's the probability of a given person having blood pressure greater than 130? In other words, what area under the curve is above 130? So our x is equal to 130. We want to convert this to a value of z. Using our formula of x minus the mean divided by the square root of the variance, we get 130 minus 120 divided by the square root of 100. The answer is 1. So now instead of asking what's the probability that x is greater than 130, we're asking what's the probability that z is greater than 1. And so as we saw in the previous slide, the area under the curve between the mean of 0 and z equal to 1 on the right-hand side is 0.3413. But we want to know the area to the right of 0.3413 because we want to know the probability that z is greater than 1. So to get this, we simply subtract 0.3413 from 0.5 to get our answer of 0.159. In other words, the probability of a given person randomly selected in a healthy population having blood pressure greater than 130 is 15.9%. Second example, what's the probability of a person having blood pressure between 110 and 130? So we're interested in the area under the curve between 110 and 130. So the probability that x is greater than 110, less than 130. So we want to find the probabilities for z. So I've filled in the formulas there for x on either side of z that we're interested in. And so really we're interested in the probability that z is greater than -1 and less than 1. And so the area under the curve between z and between a z-score of -1 and the mean of 0, remember the z of -1 is to the left of the mean, is equal to 0.3413. So it's the same as the distance between the mean and z equal to 1. And so we add these up because we're interested in the entire area under the curve between z equal 1 and between z equals to -1 and z equals to 1. And so when we add these up, the probability that z is greater than -1, less than 1 is 0.683. And so the probability of a person in our distribution having blood pressure between 110 and 130 is 68.3%. So here, I'm not going to go through this slide in painstaking detail. I've provided it for your reference. This is a recipe for using z-scores with the standard normal table. I've also put this into a Word document that I'm including in the folder for this module for you to use, because I'm going to, in the homework, have you calculate these z-scores. The main steps are to compute z, standardizing your x value, look it up in the standard normal table to get the associated probability, and you'll want to do some things a little differently depending on whether your z-score is positive or negative. Remembering, keep that picture of the distribution in mind and thinking about which side of the mean zero it falls on. And depending on your question, you're going to add up or subtract those probabilities differently. And then also, if you're trying to find a range of z-scores, then you're going to need to compute two numbers. And the probabilities are going to depend on whether your range overlaps zero or whether it doesn't overlap zero but is entirely in one of the two sides of the distribution. Okay, so fortunately there is also a normal approximation to the binomial distribution that we talked about in the previous lecture. Interestingly, the binomial distribution becomes more symmetric and bell-shaped as the sample size n increases, and especially as the proportion of successes signified by pi approaches 0.5. And by the central limit theorem that we'll discuss in the next lecture, the sampling distribution of means for large samples also resembles the normal distribution, even if the proportion isn't very close to 0 or 1. But if n is large, the binomial distribution still becomes close to a normal distribution. So why should you care? What this means is that you can use z-scores and our handy table to compute binomial probabilities instead of doing them by hand. And so the equation for standardizing a binomial variable, the random variable referred to as x, for instance, our coin flip, here's the equation for standardizing it and getting the z-score. It's equal to x minus the number of trials multiplied by the probability of success on any trial, that's in the numerator, divided by the square root of n multiplied by pi multiplied by 1 minus pi. And that's how you get your z-score. In some situations, rather than working with the number x of successes in n trials, we might just have the fraction of successes in n trials. And so that's denoted by the letter f, and f is simply equal to x divided by n. And so here's the formula for calculating the z-score with the fraction of successes. So f minus pi over the square root of pi multiplied by 1 minus pi divided by n. And then you can see the equations for the mean, variance, and standard deviation of the binomial fraction of success there as well. The main thing being know how to calculate z. Once you got z, you're golden because you can look it up in that handy table.